Imagine looking back at the Earth from the deep silence of space, seeing a singular glowing marble of blue. It hangs there, suspended in a velvet void. This vibrant sphere formed roughly 4.54 billion years ago from the swirling dust and gas of the solar nebula. If you enjoy learning about our home through these relaxing facts, subscribing helps us keep this atlas growing. Earth is far from a static object, as it is currently hurtling through the cosmic dark at an incredible 67,000 miles per hour. This velocity is necessary to maintain a stable orbit around the Sun, representing a delicate balance between gravitational pull and forward momentum. We reside within the circumstellar habitable zone, often called the Goldilocks zone, where the temperature is just right for liquid water to persist on the surface. NASA planetary scientists note that even a slight shift in our orbital distance could render the planet either a frozen wasteland or a pressurized furnace. Consider this a mental atlas, a quiet tour of the globe designed for bedtime listening as we drift across continents and through the deep mantle. The Earth's crust, where all known life exists, is surprisingly thin, comparable to the skin of an apple when measured against the planet's total radius. Deep beneath that skin, the core burns as hot as the surface of the Sun, reaching temperatures over 10,000 degrees Fahrenheit. This internal heat, a remnant of the planet's violent birth and the decay of radioactive elements, drives the movement of tectonic plates. Our planet is the only celestial body known to harbor an atmosphere rich in free oxygen, which is a byproduct of billions of years of biological activity. It is shielded by a powerful magnetosphere generated by the churning liquid iron in its outer core, which deflects the relentless solar wind. Without this invisible shield, our atmosphere would have been stripped away long ago, leaving a barren landscape. The Earth's axial tilt of approximately 23.5 degrees is what gives us our seasons, ensuring that heat is distributed across the latitudes over the course of a year. Geological records indicate that Earth has survived 5 major mass extinction events, yet it remains a resilient, closed system. It is the densest planet in our solar system, largely due to its massive metallic core and high concentration of heavy elements like iron and nickel. Every mountain range and ocean trench is a testament to the slow, steady work of deep time. As we transition from the global view to the specific wonders of the terrain, we begin to see the planet as a living, breathing geological engine. This engine defines itself first through its physical form, which is far more complex than a simple classroom globe suggests. While we often imagine our world as a smooth, perfect sphere, the rapid rotation of the planet creates an outward centrifugal force that causes the equator to bulge. This distortion turns the Earth into what scientists call an oblate spheroid, flattened slightly at the poles and wider around its middle. If you were to stand at the North Pole, you would actually be about 21 kilometers closer to the center of the Earth than if you were standing on a beach in Ecuador. This subtle shift in geometry is the first hint that the forces governing our world are not distributed with perfect symmetry. Beyond the physical surface lies an invisible, undulating map known as the geoid. Do you remember looking at a globe as a child and wondering if the blue parts were perfectly level with the green parts? This geoid represents the shape the ocean's surface would take under the influence of Earth's gravity and rotation alone, if other influences such as winds and tides were absent. It is essentially a surface of equal gravitational potential. Because the interior of the planet is not uniform, with varying densities of rock and pockets of heavy metals, the pull of gravity changes depending on where you are standing. If you find these relaxing facts helpful for your rest, subscribing is a wonderful way to support more bedtime listening. Imagine the Earth not as a solid marble, but as a lumpy potato of varying weights. One of the most famous examples of this gravitational inconsistency is found in the Hudson Bay region of Canada. For decades, researchers noted that gravity in this area is significantly lower than the global average. Part of this phenomenon is due to the lingering effects of the last ice age. The massive weight of the Laurentide ice sheet once compressed the crust, and the ground is still very slowly rebounding upward. This displacement of mass creates a subtle hollow in the local gravity field. Another contributing factor involves deep mantle convection currents that pull mass away from the crust in that specific location. These variations are vital for calibrating satellites and understanding sea level change. Data from the NASA GRACE mission has mapped these anomalies with incredible precision, showing us that our planet's grip on us is a shifting, dynamic thing. As we look deeper, we realize that the same gravity responsible for these subtle lumps is also the primary architect of the planet's internal structure. It is the invisible hand that sorts the heavy from the light, pulling the dense iron core tight while allowing the lighter crust to float above. This tension between mass and motion provides the scaffolding for every mountain and valley. Beneath this surface scaffolding, the world transforms into a series of concentric layers defined by increasing heat and staggering pressure. We understand these hidden depths not through direct sight, but through the rhythmic echo of seismic waves traveling through the Earth's vast body. When an earthquake occurs, it sends out vibrations that act like a planetary ultrasound, revealing the hidden densities of materials thousands of miles below. Scientists like Ing Lehman and Richard Dixon Oldham discovered that these waves behave differently as they hit the center, leading us to realize the core is not a single uniform mass. The outer core is a churning liquid ocean of iron and nickel, roughly 2,200 kilometers thick. It is here, in this sweltering subterranean sea, that the temperature begins to rival the intensity of the atmosphere of distant stars. This liquid layer is in constant, turbulent motion, driven by the planet's rotation and the steady escape of heat from the deep interior. Do you find it strange to think of a liquid ocean made of metal spinning far beneath your bed? This fluid motion creates the geodynamo, an intricate engine that generates the Earth's magnetic field. This invisible shield reaches far into space, deflecting the harsh solar wind that would otherwise erode our atmosphere and leave the world a barren wasteland. As we descend further into the center of the Earth, the pressure becomes so unimaginable that the common laws of chemistry seem to bend. At the very center lies the inner core, a solid ball of iron and nickel about 1,200 kilometers in radius. It is nearly as large as the moon and glows with a white-hot intensity of roughly 5,400 degrees Celsius. In any other environment, this temperature would vaporize metal instantly. However, the weight of the entire planet pressing inward creates a force over 3 million times greater than the air pressure we experience at sea level. This crushing gravity forces the atoms together so tightly they cannot melt, locking them into a solid crystalline lattice. This solid heart is not static. Evidence from seismic data suggests it may rotate at a slightly different speed than the crust above, a phenomenon known as superrotation. Every year, as the planet very slowly sheds its primordial heat into space, a thin layer of the liquid outer core freezes onto the surface of the solid inner core. This process of crystallization releases even more heat, which helps sustain the convection currents in the liquid layer above. We are essentially living on top of a giant cooling battery that has been discharging for 4.5 billion years. Seismic data from the United States Geological Survey and various global networks indicates that the very center of the inner core may even contain a distinct sublayer with different crystal alignments. This innermost inner core hints at a complex history of cooling and shifting that we are only beginning to decode through the study of primary and secondary waves. The transition from the solid crust to the liquid mantle and finally to this metallic heart represents a journey through the fundamental physics of our existence. It is the weight of everything above that creates the stability of the center, a paradoxical balance where the most extreme conditions provide the foundation for the life-sustaining magnetic field. As this heat slowly migrates toward the surface, it fuels the tectonic movements that keep our world geologically active and vibrant. This movement within the metallic depths does more than just shift the continents above. It generates a protective cocoon that reaches far into the vacuum of space. Within the liquid outer core, the churning of molten iron and nickel acts as a massive planetary generator, a process scientists call the geodynamo. As the Earth rotates, these vast rivers of liquid metal are twisted into spiral patterns by the Coriolis force, creating a complex web of electrical currents. These currents, in turn, produce a magnetic field that envelops the entire planet, extending tens of thousands of kilometers into the dark reaches of the solar system. Without this invisible barrier, known as the magnetosphere, the relentless stream of charged particles from the sun would scour our atmosphere away over millions of years. This solar wind, composed of high-energy electrons and protons, is diverted around the Earth like water flowing past the bow of a ship. It is fascinating to imagine that an invisible force, born from the heat beneath our feet, is the only thing standing between us and the harsh radiation of deep space. Have you ever looked at a compass and wondered about the invisible lines of force guiding its needle? This magnetic orientation is not a static feature of our world, as the magnetic North Pole is constantly on the move, drifting away from its geographic counterpart. Currently, the magnetic North Pole is migrating from the Canadian Arctic towards Siberia at a pace of roughly 50 kilometers per year. This wandering occurs because the liquid flows in the outer core are turbulent and ever-changing, causing the magnetic field to fluctuate in strength and orientation. Over vast geological timescales, the poles have even swapped places entirely, an event known as a geomagnetic reversal, which leaves a permanent record in the cooling lava of the ocean floor. While the magnetic field fluctuates, it remains anchored to the core, acting as the primary guardian for the layers above. Moving upward from this churning sea of molten metal, we encounter the boundary of the mantle, the single largest component of our planet's interior. This massive layer accounts for approximately 84% of the Earth's total volume, stretching nearly 3,000 kilometers toward the crust. It is not a liquid like the outer core, nor a simple solid like the rocks we find on the surface, but a complex, high-pressure environment of silicate minerals. The mantle represents a slow-moving engine of heat where solid rock behaves like a viscous fluid over millions of years. In this state of plastic flow, the mantle carries the warmth of the deep interior toward the surface in a silent, grand procession of matter and energy. This process of convection is the heartbeat of the Earth, driving the slow drift of tectonic plates and the violent release of volcanic eruptions. As we transition into this vast rocky middle, the pressure reaches such intensity that the minerals themselves must change their molecular structure to survive the weight of the world above. This phase transition creates a denser, more compact material known as bridgmanite, a mineral that researchers at the Smithsonian and various geophysical laboratories identify as the most abundant substance on our entire planet. Beneath our feet, for nearly 3,000 kilometers, the mantle stretches as a silent, heavy titan composed primarily of silicate rocks rich in magnesium and iron. Unlike the rigid crust we walk upon, the mantle exists in a perpetual, agonizingly slow motion. We often imagine the interior of the Earth as either solid stone or liquid fire, but the reality is far more curious. It behaves with a quality called plasticity, a mechanical property where solid matter flows under extreme pressure over vast stretches of time. Think of it not as a splashing sea, but as a dense, dark syrup or a thick glacial ice that yields only when measured in centuries. The silicate minerals here, particularly olivine and pyroxene in the upper regions, are squeezed so tightly that they retain a solid crystalline structure even as they migrate. This balance between heat and pressure is delicate. While temperatures in the lower mantle can soar toward 4,000 degrees Celsius, the crushing weight of the layers above prevents the rock from melting into a true liquid. Instead, it becomes a rade, which is a solid that flows. Do you ever wonder if the ground beneath your home feels more like a permanent foundation or a slow-moving vessel? This massive reservoir of heat and rock acts as the primary engine of our world. It is powered by two distinct sources: the primordial heat left over from the Earth's violent birth and the constant, invisible decay of radioactive isotopes like uranium, thorium, and potassium. This internal furnace creates a phenomenon known as mantle convection. In a cycle that can last hundreds of millions of years, the hottest material near the core mantle boundary becomes slightly less dense and begins a slow, majestic ascent toward the surface. Because the lithosphere is cooler and more brittle than the material beneath it, it fractures under pressure, creating the distinct boundaries that define our geological history. This constant motion is driven by the immense internal heat of the Earth, which generates convection currents similar to the slow rolling of water in a heated pot. While it may seem that the ground beneath us is a symbol of permanence, it is actually in a state of perpetual, measured flight. The speed at which these plates migrate is surprisingly familiar, moving at roughly the same pace as your fingernails grow each year. This translates to an average movement of just a few centimeters annually, a rate so gradual that it remains invisible to the human eye without the aid of precise satellite measurements. Despite this agonizingly slow pace, the sheer mass of these plates means they possess an incredible amount of momentum. Over millions of years, these tiny increments add up to thousands of miles, rearranging the world's geography entirely. If you could speed up time, you would see the continents dance across the blue expanse of the oceans, merging and splitting in a slow-motion ballet. Do you remember looking at a map as a child and noticing how South America seems to fit perfectly into the curve of Africa? This observation is a gateway to understanding how the world was once a single landmass. These interactions between plates occur primarily at their edges, where three distinct types of boundaries dictate the landscape's evolution. In places like the mid-Atlantic ridge, plates are pulling away from each other at divergent boundaries, allowing fresh molten magma to rise from below and solidify into new crust. Elsewhere, plates collide at convergent boundaries, where one slab might be forced beneath another in a process called subduction. These zones are often marked by deep ocean trenches and chains of volcanic islands that rise from the depths. The third type, known as transform boundaries, occurs when plates slide horizontally past one another, catching and releasing with enough energy to cause the ground to tremble. Amidst the vastness of our solar system, this active recycling of the planet's surface is a rare and precious phenomenon. Earth is currently the only known planet that possesses active plate tectonics, a feature that many scientists believe is essential for maintaining a habitable environment. This process acts as a planetary thermostat over geological timescales. Our world's unique restlessness is a sign of its internal vitality, a heartbeat of stone that keeps the planet alive. This internal energy finds its most dramatic expression along the edges of the Pacific Ocean, in a vast horseshoe-shaped belt known as the Ring of Fire. This region contains over 75% of the world's active volcanoes and is responsible for the vast majority of our planet's seismic activity. It is a place where tectonic plates are constantly colliding or sliding beneath one another in a process called subduction. As one plate sinks into the hot mantle, it carries water and minerals that lower the melting point of the surrounding rock, creating pockets of buoyant magma. This molten rock eventually forces its way upward, piercing the crust to form the towering peaks we recognize as volcanoes. Many of the mountains in this region are stratovolcanoes, characterized by their symmetrical, steep-sided cones and a history of violent, explosive eruptions. The magma within these giants is thick and viscous, often rich in silica, which traps gases under immense pressure until the structure can no longer contain them. When they finally vent, they release massive plumes of ash and pyroclastic flows that can reshape the landscape in a matter of hours. Have you ever stood near the base of a mountain and felt the weight of its silent, ancient power? In stark contrast to these explosive giants are the shield volcanoes, which resemble a warrior's shield laid flat upon the ground. These structures, like the massive Mauna Loa in Hawaii, are built almost entirely of fluid basaltic lava flows that travel long distances before cooling. Because the lava is thin and low in silica, gases escape easily, leading to steady, effusive eruptions rather than sudden blasts. These eruptions are the primary architects of oceanic islands, slowly layering stone upon stone over millions of years until they breach the surface of the sea. While terrestrial eruptions capture our imagination, the vast majority of Earth's volcanic activity occurs unseen, deep beneath the ocean waves. Along the mid-ocean ridges, the crust is literally pulling apart, allowing magma to rise from the mantle and fill the void. This process of seafloor spreading creates thousands of miles of new volcanic crust every year, often forming distinctive rounded shapes known as pillow lavas. These underwater vents also support unique ecosystems that thrive in the chemical-rich heat far removed from the reach of the sun. As this red-hot magma meets the cold touch of the atmosphere or the sea, it undergoes a rapid phase change, crystallizing into solid igneous rock. This transition from liquid fire to solid earth is the fundamental mechanism of planetary growth and renewal. Each new layer of basalt or andesite represents a fresh page in the geological record, a testament to the planet's ability to recycle its own interior. This cooling process is not just an ending, but a beginning for new land masses and the minerals that will eventually support life. If you enjoy learning about these quiet, massive shifts in our world, you might consider subscribing to hear more stories of our planet's evolution. The persistence of this volcanic cycle ensures that the Earth remains a dynamic, evolving stage, never static and always in the process of becoming something new. This cooling and solidification of rock also releases essential gases into the atmosphere, contributing to the air we breathe and the water that fills our oceans. This degassing process, occurring over billions of years, helped create the very atmosphere that protects us today. The mineral-rich soil that results from weathered volcanic rock is some of the most fertile on Earth, supporting dense forests and vast agricultural regions. Even in its destruction, the volcano is a harbinger of life, providing the raw materials necessary for ecosystems to flourish. This cycle of heat and stone is the furnace of our world, an ancient system of vents that allows the planet to breathe and rebuild itself from the inside out. As the land cools and stabilizes, it prepares the way for the next great force of nature to leave its mark. Where the folding of the Earth's crust begins, the cooling land meets the irresistible momentum of drifting tectonic plates to create the Great Mountains. This process, known as orogeny, represents the most dramatic physical transformation of our planet's surface. Think of the colossal power required to lift the floor of an ancient ocean thousands of feet into the thin, cold air of the stratosphere. This is exactly what occurred when the Indian subcontinent, once an island mass, migrated northward across the Tethys Sea at what geologists consider a high speed. When it finally collided with the massive Eurasian plate roughly 50 million years ago, the impact was so slow and powerful that the crust had no choice but to wrinkle and stack. The result was the Himalayas, a range so vast it influences global weather patterns and jet streams even today. Within these jagged peaks, marine fossils of ancient sea creatures can still be found near the summit of Mount Everest, offering silent proof that the highest point on Earth was once a quiet seabed. These mountains continue to grow even now, rising by several millimeters every year as the tectonic pressure persists beneath the soil. Have you ever looked at a map and noticed how the continents seem to fit together like a puzzle? Beyond the crashing of land masses, mountains also rise through the silent descent of the ocean floor. Along the western edge of South America, the dense Nazca Plate slides beneath the lighter continental crust in a process called subduction. This friction generates intense heat, melting rock into magma that fuels the volcanic arc of the Andes. While volcanoes add height from above through eruptions, the compression of the plates simultaneously squeezes the land into the longest continental mountain range in the world. Yet the height we see above the clouds is only a small fraction of the total mass involved in these structures. Just as a massive iceberg hides the majority of its bulk beneath the surface of the sea, a mountain relies on a hidden foundation known as a root. This is the principle of isostasy, a fundamental concept in geology that describes how the Earth's lithosphere floats on the more ductile, plastic-like mantle below. For every towering peak that reaches towards the stars, there is a deep reservoir of low-density crust pushing down into the mantle to maintain buoyancy and balance. If a mountain loses weight through the natural process of erosion, the crust actually springs upward to compensate, a slow-motion rebound that keeps the heights elevated for millions of years. This gravitational equilibrium ensures that the planet's surface remains stable despite the immense weights shifting across its face. However, as quickly as the Earth builds these monuments, the elements begin a relentless campaign to dismantle them. Gravity, ice, and wind are the patient sculptures that turn jagged peaks into rolling hills over incomprehensible spans of time. The destruction of these heights is not a loss, but a transition, as the stones of the summit begin their long journey back toward the sea. This descent is driven by the dual forces of weathering and erosion, processes that work in tandem to reshape the entire crust. While weathering breaks the rock apart where it stands, erosion acts as the transport system that carries the debris away. The Grand Canyon stands as a silent monument to this persistence, where the Colorado River has carved a mile-deep chasm through the Kaibab Plateau. Each ripple in the water carries away a tiny portion of the canyon floor, a process that has moved millions of tons of silt toward the Gulf of California. Think back to a time when you sat before a vast mountain range or a deep, quiet valley. What about that landscape brought you a sense of stillness? The stillness we perceive in these places is actually a facade for constant microscopic movement. Physical weathering, or mechanical breakdown, occurs when the environment exerts force directly onto the stone. In high-altitude environments, the freeze-thaw cycle is a dominant sculptor. Water trickles into the smallest fissures during the day and expands by nearly 9% as it turns to ice overnight. This expansion acts like a wedge, exerting thousands of pounds of pressure per square inch, slowly prying the rock apart until it yields. Over centuries, these repeated cycles can reduce a solid granite face into a slope of jagged scree. Even the lightest breeze plays its part, picking up microscopic grains of quartz and hurling them against cliffsides. This natural sandblasting smooths out edges and creates the arched bridges and hoodoos found in arid deserts, proving that even the lightest breeze holds the power to reshape the Earth. Chemical weathering operates with a different kind of subtlety, altering the very molecular structure of the minerals involved. When rain falls through the atmosphere, it picks up carbon dioxide, forming a weak carbonic acid that reacts with certain types of stone. Limestone landscapes are particularly vulnerable to this, as the acidic water dissolves the calcium carbonate, creating vast underground cavern systems and dramatic sinkholes. This process of carbonation locks away atmospheric carbon into the seafloor as sediment. Oxidation is another chemical path where oxygen reacts with iron-bearing minerals to turn mountainsides a deep, rusty red. As these rocks weaken and crumble, they eventually break down into the fundamental components of soil. Biological weathering contributes further, as the roots of a single tree can find a hairline fracture and exert enough biological force to split a boulder in two. Lichens and mosses also play a role, secreting organic acids that slowly eat away at the stone surfaces they inhabit. Eventually, the once mighty peaks are ground down into the silt and clay that form the fertile plains where life thrives. Every grain of sand on a distant beach was once part of a high summit, transported by the relentless flow of water and gravity. The cycle of erosion ensures that no feature on Earth is permanent, but rather a temporary shape in a world that is constantly recycling itself. Beneath the visible horizon lies a hidden architecture carved by the patient chemistry of water and stone. This subterranean realm begins with the simple interaction of rain and air as falling droplets absorb carbon dioxide to form a weak carbonic acid. When this slightly acidic water seeps into the ground, it encounters vast beds of limestone, a sedimentary rock composed largely of the compressed remains of ancient marine organisms. Over eons, the acid dissolves the stone along tiny cracks and fissures, slowly widening them into the labyrinthine galleries of karst landscapes. These hidden voids can eventually collapse, creating the dramatic sinkholes that pockmark the surface of regions like Florida or the Yucatan Peninsula. Within these hollows, the air is heavy with moisture and the scent of damp minerals. Here, the process of creation mirrors the process of destruction, as dissolved calcium is redeposited in delicate crystalline structures. Stalactites reach down from the ceiling like frozen stone icicles, while stalagmites rise from the floor to meet them. Have you ever stood in a vast, quiet space and felt the weight of the silence around you? When these two formations finally touch, they fuse into a single solid column, a monument to thousands of years of steady, rhythmic dripping. In the darkness of Mammoth Cave in Kentucky, researchers have mapped more than 400 miles of interconnected passageways, making it the longest known cave system on our planet. This massive network remains entirely shrouded in a perpetual night that has never seen a single ray of sun. Such environments have birthed a specialized caste of inhabitants known as troglobites, creatures that have evolved to thrive where light is entirely absent. Many of these species, including certain cave fish and salamanders, have completely lost their eyes and skin pigment through millions of years of adaptation. They navigate their silent world using heightened senses of touch, smell, and vibration, sensing the slight movement of water from several feet away. The temperature inside a deep cave remains remarkably stable, typically matching the average annual temperature of the land directly above it. This thermal consistency makes caves important archives for paleoclimatology, as the layers of minerals in stalagmites can reveal the rainfall patterns of the distant past. Each thin band of calcite acts like a microscopic library, preserving chemical signatures of the Earth's atmosphere from hundreds of millennia ago. Beyond limestone, some caves are formed by the presence of sulfuric acid, which can hollow out massive rooms in a fraction of the time required by carbonic acid. The Lechuguilla Cave in New Mexico features rare gypsum chandeliers that grow up to 20 feet long, looking like translucent ribbons of silk. These formations are so fragile that a single human breath can alter the humidity enough to damage them. This world beneath our feet is not a static tomb, but a slow-motion lung, breathing in the surface waters and exhaling them back into the rivers and springs that sustain our lives. Exploring these depths provides a profound sense of scale, reminding us that the Earth is not just a surface to inhabit, but a deep and complex volume with secrets tucked away in the cold, quiet dark. Emerging from the cool shadows of the Earth, we find ourselves standing beneath an expansive sky where the air is thin, dry, and filled with the scent of sun-baked stone. Deserts cover nearly 1/3 of our planet's land surface, defined not by their heat, but by a chronic lack of moisture known as aridity. While popular imagination often conjures images of endless, rolling orange sand dunes, the reality of the Sahara is far more diverse and rugged. Only about 25% of this massive desert consists of sand, a landscape known as an erg. The remainder is a stark mosaic of gravel-covered plains called regs and high, wind-swept rocky plateaus known as hamadas. These stone-strewn vistas have been sculpted by the wind for millions of years, leaving behind a resilient pavement that protects the soil beneath from further erosion. Have you ever stood in a wide, open space and felt the profound silence of a world without wind or water? If you find value in these quiet explorations of our world, subscribing helps us continue mapping the wonders of the Atlas together. Moving westward across the Atlantic to the narrow strip of land between the Andes Mountains and the Pacific Ocean, we encounter the Atacama Desert. This is the driest non-polar place on Earth, where some weather stations have never recorded a single drop of rainfall in their entire history. The environment is so intensely desolate and chemically similar to the Red Planet that NASA frequently uses the Atacama to test instruments intended for Mars rovers. Because the air is so exceptionally clear and devoid of water vapor, it serves as one of the premier locations on the globe for astronomical observation, allowing us to peer into the deep reaches of space with unparalleled clarity. Life in these extreme reaches has evolved through ingenious biological engineering to survive where others would perish. The fennec fox sports oversized ears that act as natural radiators, dissipating body heat into the surrounding air to keep its internal temperature stable. Plants like the saguaro cactus have developed a pleated skin that allows them to expand rapidly like an accordion when rare rains arrive, storing hundreds of gallons of water within their pulpy interior. Even the iconic camel has mastered survival, not by storing water in its humps, but by storing concentrated fat that can be metabolized into energy and water when resources are scarce. Do you prefer the warmth of a dry summer afternoon or the crispness of a cool autumn morning? While we often associate these landscapes with blistering heat, some of the most formidable deserts are actually quite cold. The Gobi Desert, stretching across northern China and southern Mongolia, is a high-altitude rain-shadow desert where temperatures can plummet far below freezing, and winter brings a dusting of snow rather than rain. This serves as a reminder that a desert is defined solely by its annual precipitation, typically receiving less than 10 inches per year. One of the most hauntingly beautiful phenomena in these arid lands is the sound of the singing dunes. When sand grains of a specific size and silica content slide against one another, the friction creates a low-frequency hum that can be as loud as a low-flying plane. This acoustic vibration, caused by the synchronized movement of millions of particles, reminds us that even the most silent landscapes possess a voice of their own. Leaving the singing sands behind, we move toward a land where the earth itself is submerged beneath a frozen ocean of fresh water. Antarctica is not merely a continent covered in snow, but a massive architectural feat of ice that contains approximately 70% of all the fresh water on our planet. This ice sheet is an ancient record, a crystalline library where each layer of snowfall traps tiny bubbles of atmosphere from hundreds of thousands of years ago. The sheer mass of this frozen mantle is difficult to visualize, yet its weight is powerful enough to depress the continental crust by hundreds of meters through a process known as iastatic depression. In some regions, the ice is so heavy and deep that the bedrock beneath it actually sits well below sea level. Splitting this white expanse are the Transantarctic Mountains, a range that spans some 3,500 kilometers. These peaks act as a great divide, separating the stable, high-altitude plateau of East Antarctica from the lower, more geologically active West Antarctica. Beneath the East Antarctic ice lies a hidden world of jagged relief, including the Gamburtsev subglacial mountains. These peaks are roughly the size of the Alps, yet they remain invisible to the naked eye, mapped only through the use of ice-penetrating radar. This hidden topography dictates the slow, grinding flow of the glaciers as they creep toward the Southern Ocean. This contrast of fire and ice reminds us that the continent is geologically alive beneath its frozen exterior. While the southern pole is a solid continent buried under miles of ice, its northern counterpart, the Arctic, presents a symmetrical inversion of this geography. You might enjoy following along with more of these relaxing facts by subscribing to the channel for your nightly dose of science for sleep. In the Arctic, we find an expansive ocean almost entirely enclosed by the landmasses of North America, Eurasia, and Greenland. This creates a dynamic environment where the ice is not a fixed cap on solid ground, but a floating, shifting mosaic of frozen seawater. Unlike the terrestrial ice sheets of the South, Arctic sea ice is subject to the constant whims of ocean currents and wind, causing it to crack, pile into jagged pressure ridges, and drift across the pole. Every year, this frozen crust undergoes a rhythmic pulse, expanding to cover nearly 15 million square kilometers in the deep chill of March, before retreating to its minimum extent in September. Have you ever stood on a frozen lake and heard the deep, echoing cracks of the ice shifting beneath your feet? This seasonal cycle is a critical component of the climate system because of the albedo effect. Bright white ice reflects the majority of the sun's radiation back into space, whereas the dark open water absorbs that heat, further warming the region in a process known as Arctic amplification. Beneath the immediate surface of the surrounding land, the grip of winter is even more permanent. Permafrost defines much of the Arctic landscape, consisting of soil, rock, or sediment that has remained frozen for 2 or more consecutive years. In some regions of the Siberian tundra, this frozen layer reaches staggering depths exceeding 1,000 meters. It acts as a massive subterranean refrigerator, locking away organic matter that has been preserved for thousands of years. As this ground thaws, it can release greenhouse gases like methane and carbon dioxide, which were previously trapped in the icy matrix of the soil. This thawing also reshapes the physical terrain, creating thermokarst lakes and causing trees to tilt at sharp angles in what scientists call drunken forests. Beyond the land, the Arctic Ocean reveals its own unique chemical structure. Large rivers from Russia and Canada pour immense volumes of fresh water into the basin, creating a buoyant surface layer that is significantly less salty than the deeper ocean. This salinity gradient, known to oceanographers as the halocline, acts as a barrier that insulates the surface ice from the warmer, saltier Atlantic water flowing underneath. Life here has adapted to these extreme thresholds in remarkable ways. The narwhal, often called the unicorn of the sea, possesses a sensory tusk that is actually a specialized tooth containing millions of nerve endings. Bowhead whales navigate these frigid depths with lifespans that can exceed 2 centuries, making them some of the longest-lived mammals on the planet. Even the polar bear, which we often associate with the land, is biologically a marine mammal that depends entirely on the integrity of the sea ice for its survival. As the ice continues its seasonal dance, the frozen world begins to give way to the deep circulating currents of the global ocean system. Moving westward from the icy margins, the horizon stretches into the Pacific, a body of water so immense that it encompasses nearly 1/3 of our planet's total surface. If you were to gather every single piece of dry land, continents, islands, and peninsulas, and nestle them into this single basin, there would still be millions of square miles of blue water remaining. This vast expanse acts as the Earth's thermal regulator, absorbing heat and driving weather patterns that sustain life thousands of miles from its shores. Beneath the surface ripples, the seafloor is not a flat plain, but a rugged landscape of volcanic peaks and canyons that dwarf the Himalayas. The Pacific Basin holds more than half of the world's free-moving water, creating a liquid wilderness that is often several miles deep. In the western reaches of this ocean lies the Mariana Trench, a crescent-shaped scar in the crust formed by the slow, relentless collision of tectonic plates. At its lowest point, known as the Challenger Deep, the water column exerts a crushing force of approximately 8 tons per square inch. This pressure is so intense that even the molecular structure of water slightly compresses, making the liquid at the bottom denser than at the surface. Despite the absolute absence of sunlight, this environment is not barren. Life here has adapted to survive without the energy of the sun, relying instead on marine snow, which is a constant drift of organic detritus falling from the upper layers of the sea. As we descend past the epipelagic and mesopelagic zones, we enter the midnight zone, or the bathypelagic. Have you ever seen a firefly in the summer and wondered if the same chemistry works beneath the waves? Within this eternal darkness, the temperature hovers just above freezing, and the stillness is absolute, save for the occasional spark of biological light. Approximately 90% of deep-sea creatures are thought to be bioluminescent, producing their own glow through complex chemical reactions involving the molecule luciferin. Some use this light as a lure, like the female anglerfish with her glowing dorsal fin, while others use it as a sudden flash to blind encroaching predators. The silence of the deep Pacific is a misconception, as sound actually travels 4 times faster in water than in air. Low-frequency noises, such as the songs of whales or the grinding of tectonic plates, can travel thousands of miles through a specific layer of water called the SOFR channel. This deep-sea acoustic highway allows animals to communicate across entire ocean basins using minimal energy. The seafloor itself is home to hydrothermal vents, where superheated, mineral-rich water billows from the Earth's interior into the cold abyss. These vents support entire ecosystems of tube worms and giant clams that derive energy from chemicals like hydrogen sulfide through a process called chemosynthesis. This discovery, documented by researchers at the Woods Hole Oceanographic Institution, fundamentally changed our understanding of where life can exist. The Pacific contains more than 25,000 islands, most of which are the tips of massive underwater volcanoes that comprise the Ring of Fire. This geological belt is responsible for the majority of the world's earthquakes, reminding us that the calm surface masks a restless foundation. Moving further into the depths, we find that the global ocean is a single, interconnected heart, pumping life and heat through every corner of the globe. This vast system of movement is known as the thermohaline circulation, a term derived from the Greek words for heat and salt. It operates as a silent, submerged engine, powered by the subtle interplay of temperature and salinity, which dictates the density of every drop. In the frigid reaches of the North Atlantic, surface waters lose their heat to the biting air, becoming cold and heavy. As sea ice forms, it leaves behind its salt, further increasing the weight of the surrounding liquid. This dense, briny water eventually plunges toward the abyss, creating a massive underwater waterfall that drives the entire global network forward. This downward surge acts as the primary pump, pushing deep water currents southward along the Atlantic basin. While the deep currents crawl through the darkness, surface currents like the Gulf Stream race across the upper layers of the sea. This powerful river of warm water originates in the tropical warmth of the Caribbean before surging northward along the eastern coast of North America. It transports more water than all the world's rivers combined, acting as a colossal radiator for the northern hemisphere. Without this constant influx of warmth, the climates of Western Europe and the United Kingdom would be significantly colder, resembling the icy landscapes of subarctic Canada. Have you ever stood on a shoreline and wondered where the water at your feet might have been a century ago? The scale of this journey is almost impossible to fathom from our perspective of minutes and hours. A single parcel of water entering the conveyor belt in the North Atlantic may take a full millennium to return to its starting point. It travels thousands of miles, descending into the deep Southern Ocean, swirling around Antarctica, and eventually rising back to the surface in the North Pacific through a process called upwelling. This slow, deliberate pace ensures that the ocean acts as a massive thermal buffer, absorbing and redistributing the sun's energy over centuries. It is a planetary-scale recycling system, replenishing nutrients and oxygen in the deep while regulating the atmospheric chemistry we depend on for every breath. As these currents meander through the deep, they are not moving through a featureless void. They are guided and shaped by the complex topography of the seabed, which acts as a series of walls and valleys for the water to navigate. The very shape of the continents and the hidden mountain ranges beneath the waves determine the path of this eternal flow. Understanding the movement above requires us to look even deeper, toward the rugged architecture of the Earth's crust itself. Beneath the churning currents lies a landscape as varied and dramatic as any found on dry land, where the story of our planet is written in basalt and silt. Deep within this lightless realm exists the mid-ocean ridge, a continuous chain of volcanic mountains that stands as the longest mountain range on our planet. While the Andes or Himalayas may occupy our terrestrial imagination, this submerged giant stretches for over 40,000 miles, winding through the Atlantic, Indian, and Pacific Oceans like the intricate stitching on a leather baseball. It is a world formed not by the slow wear of erosion, but by the raw, constructive power of the Earth's mantle reaching toward the cold seawater. At the heart of the Atlantic, the ridge marks a divergent boundary where the North American and Eurasian plates are slowly, relentlessly drifting apart. This movement occurs at a pace nearly identical to the growth of human fingernails, roughly 1 inch every year. Yet over geological epochs, it has birthed entire oceans. Have you ever wondered what it would feel like to stand on a piece of ground that did not exist just a few decades ago? These algae perform photosynthesis, converting sunlight into energy that they share with their host. In exchange, the coral provides the algae with a protected environment and the compounds necessary for photosynthesis to occur. This relationship is so efficient that it allows reefs to grow in nutrient-poor waters where other life might struggle to survive. Over thousands of years, these polyps secrete calcium carbonate to form hard skeletons that accumulate into the massive limestone foundations we recognize today. Every intricate branch and brain-like fold is the result of countless generations of these tiny architects working in slow, rhythmic succession. Have you ever wondered what it would be like to drift weightlessly through these underwater gardens? A single reef can be home to thousands of different species, from primary producers to apex predators like reef sharks. The complexity of the architecture provides millions of crevices where small fish can hide from larger hunters. In these bustling communities, biodiversity rivals that of the tropical rainforests on land. Some corals grow less than an inch per year, making the massive structures we see today tens of thousands of years old. The Great Barrier Reef itself began forming on the continental shelf roughly 20,000 years ago during the last glacial maximum. As sea levels rose, the corals grew upward to remain within the sunlit zone, where their symbiotic algae could survive. This delicate balance of light and depth is critical for the survival of the reef system. If the water becomes too deep or too turbid, the algae cannot photosynthesize and the coral colony begins to starve. Interestingly, some corals produce their own fluorescent proteins that act as a natural sunscreen to protect them from intense ultraviolet radiation. These proteins create the vibrant, glowing colors that make certain reefs look like neon landscapes under specialized lighting. Beneath the surface, the sound of a healthy reef is a constant crackling noise, often produced by snapping shrimp and the scraping of parrotfish teeth against the stone. Parrotfish play a vital role in this ecosystem by grazing on algae that might otherwise smother the coral. As they eat, they inadvertently consume bits of the calcium carbonate skeleton, which is processed through their bodies and excreted as fine white sand. A single large parrotfish can produce hundreds of pounds of sand every year, contributing significantly to the formation of tropical beaches. This cycle of growth and decay is part of a larger geological process where reef structures eventually break down and contribute to the sedimentary layers of the earth. Many of the limestone mountains seen on land today were once vibrant coral reefs at the bottom of ancient seas. These fossilized remains allow scientists to study past climates and ocean conditions from millions of years ago. The resilience of these systems is currently being tested as ocean temperatures rise and seawater becomes more acidic due to increased carbon dioxide levels. When the water becomes too warm, the symbiotic bond between the polyp and the algae breaks, leading to a phenomenon known as bleaching. While a bleached reef is not yet dead, it is in a state of extreme stress and remains vulnerable to disease. Understanding these fragile connections is essential for preserving the biological heritage of our oceans for future generations. These living monuments remind us that even the smallest organisms can reshape the very face of our planet. From these microscopic architects of the reef, we turn our gaze toward the powerful veins of the continents, known as the rivers. These great terrestrial flows act as a global circulatory system, moving fresh water and vital minerals across thousands of miles of diverse landscapes. If you find these relaxing facts helpful for your rest, feel free to subscribe to support our exploration of the natural world. The Amazon River stands as the undisputed titan of these waterways, discharging more water than the next 7 largest rivers combined. This massive volume represents approximately 1/5 of the total river flow entering the world's oceans every single second. Scientists at the Amazon River Project have documented that the force of this discharge pushes a freshwater plume hundreds of miles into the salty Atlantic. High above the canopy, a different kind of river flows through the atmosphere in the form of massive vapor clouds. These flying rivers are generated by the transpiration of billions of trees, recycling moisture back into the air with staggering efficiency. A single large tree in the rainforest can release up to 1,000 liters of water in a single day through its leaves. This humidity travels thousands of miles, eventually falling as rain to nourish distant agricultural regions that would otherwise be arid. Moving across the globe to the African continent, the Nile River stretches over 4,000 miles from its headwaters to the Mediterranean Sea. It is a rare example of an exotic river, one that maintains its flow while crossing a vast hyper-arid desert. Most waterways would vanish under the relentless evaporation of the Sahara, yet the Nile persists due to its powerful sources in the tropical highlands. When you are settling in for the night, do you find the steady patter of rain or the constant babble of a running stream more conducive to your sleep? The journey of a river often concludes with the intricate formation of a delta, a landscape sculpted by the physics of moving water. As a river meets the sea or large lake, its velocity drops significantly, causing it to lose the energy required to carry its heavy load of sediment. This process of deposition creates vast fan-shaped landforms composed of nutrient-rich silt and alluvium. The Mississippi River Delta serves as a prime example of this geological engineering, where layers of mud have built up over thousands of years. These fertile plains provide some of the most productive soil on Earth, supporting complex ecosystems and human civilizations alike. Every grain of sand and speck of clay carried by the current has a story beginning in distant mountains and ending in the quiet marshes of the coast. The chemistry of this silt is incredibly dense, packed with minerals like phosphorus and nitrogen that feed the microscopic life at the base of the food chain. This constant movement of material ensures that the coastline is never static, but always expanding and retreating in a rhythmic dance. Understanding the hydrology of these systems helps us appreciate how the planet balances its resources, moving life-giving water from the peaks to the shore. These arteries of the Earth demonstrate that even the hardest stone can be carved by the patient, persistent force of gravity and time. When those rushing currents finally find a basin to settle in, the landscape shifts from momentum to a state of profound, silent reflection. In the heart of Siberia lies Lake Baikal, a massive rift valley that holds approximately 20% of the world's unfrozen surface freshwater. This ancient basin reaches staggering depths of over 1,600 meters, earning its status as the deepest and oldest lake on our planet. Because it has remained isolated for 25 million years, it has become a unique evolutionary laboratory, hosting the world's only freshwater seals, known as NERPA. The clarity of Baikal is legendary. During the winter, the ice is so transparent that it looks like solid glass suspended over a dark, infinite void. Far across the globe, the Great Lakes of North America represent a much younger geological story, etched into the continent by the immense weight of retreating glaciers. As the massive Laurentide ice sheet melted roughly 14,000 years ago, it left behind deep depressions that were filled by the surging meltwater. These 5 interconnected bodies of water are so vast they create their own microclimates, generating lake-effect snow and influencing weather patterns across thousands of miles. Have you ever stood on the shore of a lake so wide that the horizon looks like the edge of a great ocean? If you were to empty Lake Superior, its volume could cover the entire surface of North and South America in 1 foot of water. While these giants are filled with life-giving fresh water, other basins serve as terminal points where water evaporates and leaves concentrated minerals behind. The Dead Sea, situated at the lowest land elevation on Earth, contains a salt concentration nearly 10 times higher than that of the open ocean. This extreme salinity increases the water's density to a point where the human body becomes incredibly buoyant, making it impossible to sink beneath the surface. Similarly, the Great Salt Lake in Utah acts as a remnant of the prehistoric Lake Bonneville, where the lack of an outlet ensures that every mineral carried in by rivers stays trapped within the basin. These saline environments host resilient brine shrimp and specialized algae that can tint the water with shades of pink and purple. These reservoirs of stillness act as the planet's internal cooling systems and biological sanctuaries, trapping sediment and providing stable habitats for countless organisms. Yet water rarely stays still forever, and eventually the pressure of a full basin finds a path forward. When a lake's edge meets a sudden change in geological elevation, the potential energy stored in that quiet volume is suddenly released. This shift marks the transition into the world of falling water, where the silent mirror of the lake shatters into a roar of white mist and pure kinetic energy. Gravity takes hold of the river's path to create the vertical spectacles we recognize as the world's Great Falls. In the highlands of Venezuela, Angel Falls holds the title of the tallest uninterrupted drop on Earth, plunging 979 meters from the summit of a flat-topped Tepuy mountain. The height for this descent is so extreme that by the time the water reaches the canyon floor, much of it has atomized into a shimmering cloud of spray. This transformation from a liquid stream into airborne vapor illustrates how gravity interacts with geological height to redefine the river's physical state. If you enjoy learning about these natural wonders, subscribing helps us continue documenting the Earth's hidden mechanisms. Further south, the Zambezi River creates Victoria Falls, which stretches over a mile wide to form the largest curtain of falling water in existence. The local name for this site is Mosi Oa Tunya, which translates to the smoke that thunders, a reference to the massive plume of mist visible from many miles away. These falls are not permanent fixtures of the Earth, but rather retreating monuments that move slowly against the direction of the current. This migration happens through a process called undercutting, where the turbulent energy at the base of the fall erodes softer rock layers beneath a harder capstone. Eventually, the weight of the overhanging ledge becomes unsustainable, and the entire structure collapses into the plunge pool below. Niagara Falls provides a perfect laboratory for this geological retreat, having moved nearly 7 miles upstream since its formation at the end of the last ice age. Do you remember the first time you stood near a large body of moving water and felt that deep rhythmic vibration in your chest? Scientists at the Niagara Parks Commission note that while the falls once retreated by about a meter every year, modern hydroelectric diversions have slowed this movement to just a few inches. Even with this intervention, the falls will eventually reach the edge of Lake Erie, causing the lake to drain and the waterfall to vanish into the archives of history. As the terrain levels out and the water slows its pace, it spreads across the landscape to create the vital, quiet expanses known as wetlands. These saturated lands exist in a delicate balance between the terrestrial and the aquatic, serving as the primary filtration system for our planet's fresh water. Swamps represent the forested version of these landscapes, where water-tolerant trees like the bald cypress or the salt-hardy mangrove thrive in anaerobic mud. Marshes, by contrast, are characterized by soft-stemmed vegetation like reeds and grasses that act as physical buffers against inland flooding. Within these still waters, a complex biological process filters out toxins and traps sediments, cleaning the water before it reaches larger rivers or the open ocean. Bogs offer a more specialized environment, often forming in cold glaciated depressions where they are fed almost exclusively by rainwater. This lack of mineral-rich runoff makes bogs highly acidic and nutrient-poor, dominated by thick mats of sphagnum moss. This moss creates an environment so hostile to bacteria that organic matter does not decay in the traditional sense. Instead, it compresses into peat, a dense material that stores vast amounts of carbon for thousands of years. According to data from the International Mire Conservation Group, peatlands store twice as much carbon as all the world's forests combined. Beyond their role in climate regulation, these bogs act as accidental time capsules, preserving ancient artifacts and biological records that would have been lost in any other soil. This stillness is not an absence of life, but a concentrated nursery where 40% of the world's species find their beginning. Looking up from the vibrant nurseries of the Earth, we find ourselves at the very bottom of a vast invisible sea that stretches towards the stars. This ocean of air, known as the atmosphere, exerts a constant, gentle weight against every square inch of your skin. If you've ever felt the pressure change in your ears while traveling through mountains, you've experienced the physical reality of these gases shifting around you. At sea level, the atmosphere presses down with approximately 14.7 pounds of force per square inch, a burden our bodies are perfectly pressurized to withstand. Most of this mass is concentrated near the surface, held firmly in place by gravity's unwavering pull. If you enjoy learning these relaxing facts, you might consider subscribing to keep these quiet discoveries coming. Nitrogen makes up 78% of the air we breathe, acting as a stable diluent for the more reactive 21% that is oxygen. This delicate ratio prevents the world from becoming an inferno while ensuring life has the fuel it needs for cellular respiration. Trace gases like argon and carbon dioxide fill the remaining 1%, yet their influence on global temperatures is profound. The troposphere is the layer we inhabit, containing nearly all the planet's water vapor and weather patterns. Above this lies the stratosphere, where the air grows thinner and the ozone layer resides, absorbing the sun's harsh ultraviolet radiation. Unlike the air near the ground, the stratosphere actually warms as you ascend because of this energy absorption. Do you remember the last time you watched clouds drift by and wondered how high they were actually floating? Passing into the mesosphere, the temperature plummets to the coldest levels found in the Earth's system, reaching nearly -90 degrees Celsius. It is here that most meteors meet their end, incinerated by the friction of even this sparse collection of molecules. Higher still, the thermosphere expands, reaching temperatures that can soar to 2,000 degrees Celsius, though the air is so thin you would not feel the heat. This is where the International Space Station orbits and where the solar wind ignites the vibrant curtains of the aurora borealis. The ionosphere, a region within the upper atmosphere, is filled with charged particles that allow radio waves to bounce around the curvature of the Earth. The Kármán line sits approximately 100 kilometers above sea level, serving as the internationally recognized boundary where the atmosphere becomes too thin for aeronautical flight. Beyond this lies the exosphere, a transitional zone where individual atoms may travel hundreds of kilometers before colliding with one another. This gradual thinning means the Earth doesn't have a hard shell, but a soft, fading halo that protects us from the vacuum of the cosmos. Science for Sleep reminds us that even the space above our heads is a complex, structured machine. These bedtime listening sessions help us appreciate the thin blue line that makes our existence possible. Totaling over 5 quadrillion tons, this gaseous weight is what keeps our oceans from boiling away into the void. Within this pressurized envelope, the hydration of our planet operates through a grand, invisible architecture. Water vapor rises from the heated surface of the Earth, searching for a place to rest. It finds this sanctuary on microscopic particles known as condensation nuclei, which include specks of desert dust, volcanic ash, or even salt crystals sprayed from breaking waves. Without these tiny solid foundations, the water vapor would remain a gas, unable to coalesce into the drifting shapes we recognize. As the air rises and expands, it undergoes adiabatic cooling, a process where a drop in pressure leads to a drop in temperature. This cooling forces the vapor to cling to its microscopic seeds, forming the billions of tiny droplets that make up a single cloud. The variety of these formations depends entirely on the altitude and the temperament of the wind. High in the freezing reaches of the upper troposphere, cirrus clouds form from pure ice crystals, appearing as delicate, wispy strands that often signal a change in the weather. Below them, the mid-level altocumulus clouds often resemble a field of white wool or small ripples on a quiet pond. Have you ever found yourself gazing at a vast sheet of gray stratus clouds and wondered how many millions of gallons of water were suspended just above you? These flat, featureless layers can cover entire continents, shielding the soil from the sun's direct heat for days at a time. In contrast, the towering cumulus clouds are the visual representation of rising thermals ballooning upward into the sky like slow-motion explosions of white vapor. This entire process is part of the hydrologic cycle, a continuous loop of evaporation, condensation, and precipitation that defines the geography of life. Solar energy acts as the primary pump, lifting water from the oceans and depositing it onto the land. When the droplets within a cloud collide and merge, they gain enough mass to overcome the updrafts holding them aloft. They fall as rain, snow, or hail, carving paths through the landscape and feeding the roots of every living forest. According to researchers at NASA, the global water cycle is intensifying as the atmosphere warms, leading to more dramatic shifts between dry and wet periods across the globe. Despite these changes, the fundamental rhythm remains a constant feature of our bedtime listening. The sight of a cloud bank moving across a mountain range is a silent reminder of the atmosphere's relentless work. Each formation is a temporary vessel, a wandering atlas of the sea being carried toward the thirsty interior of the world. Watching them drift is an exercise in observing the slow, steady heartbeat of a living planet. The movement of air is governed by the rotation of the Earth, a phenomenon known as the Coriolis effect. As the planet spins on its axis, it creates an inertial force that deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This invisible hand ensures that winds do not simply move in straight lines from areas of high pressure to low pressure. Instead, they curve, creating the vast swirling patterns that dominate our weather maps and climate systems. Because the Earth is wider at the equator than it is at the poles, a point on the equator travels much faster than a point near the Arctic Circle. This difference in rotational speed is what generates the curvature, a fundamental law of fluid dynamics that influences every breeze we feel. Closer to the surface, these patterns organize into reliable corridors of movement that have guided the course of human history for centuries. The trade winds, blowing steadily from the northeast and southeast toward the equator, served as the primary engines for maritime exploration and global commerce. Sailors once relied on these consistent tropical breezes to cross the Atlantic and Pacific, mapping the world by the grace of the atmosphere. Have you ever stood on a shoreline and wondered about the distant lands that the breeze on your face visited before reaching you? Further north and south, the westerlies blow in the opposite direction, carrying weather systems from west to east across the mid-latitudes. These winds are driven by the movement of air from high-pressure cells toward the poles, creating a predictable cycle that helps balance the heat distribution of the entire globe. High above these surface winds, in the upper reaches of the troposphere, flow the jet streams. These are narrow bands of exceptionally fast-moving air, often traveling at speeds exceeding 200 miles per hour, according to the National Oceanic and Atmospheric Administration. They form at the boundaries between cold polar air and warmer subtropical air, acting as atmospheric rivers that guide the path of major storms. Commercial pilots often seek out these currents to save fuel and time, hitching a ride on a high-altitude ribbon of kinetic energy. The undulating path of a jet stream, known as Rossby waves, can trap weather systems in place for weeks, leading to prolonged periods of heat or cold. Beyond moving moisture and heat, the wind acts as a tireless sculptor of the physical world through aeolian processes. Over millions of years, the persistent friction of air and suspended particles carves intricate arches into sandstone and smooths the faces of jagged peaks. In the world's great deserts, the wind organizes billions of individual sand grains into dunes that migrate across the landscape like slow-motion waves. This transport of dust is not merely local. Mineral-rich silt from the Sahara is carried thousands of miles across the Atlantic to fertilize the Amazon rainforest. Such interconnectedness reminds us that the atmosphere is a single fluid system where a gust in one hemisphere can nourish life in another. Even the most solid rock eventually yields to the patient, rhythmic pressure of the moving air. This movement of energy manifests most powerfully in the form of a hurricane, a massive heat engine fueled by the thermal reserves of the ocean. These storms require surface waters to reach a specific threshold of approximately 80 degrees Fahrenheit to begin their development. As the warm water evaporates, it rises into the atmosphere, carrying with it a tremendous amount of latent heat. When this vapor condenses into clouds, it releases that stored heat, which further warms the surrounding air and causes it to rise even faster. This cycle creates a self-sustaining system of low pressure that can grow to be hundreds of miles wide. If you find value in these relaxing facts, subscribing to the channel is a wonderful way to support more Science for Sleep content. Because of the Earth's rotation, the Coriolis effect gives these storms their characteristic spiral, turning them counterclockwise in the northern hemisphere and clockwise in the southern. Do you find the sound of a distant storm helps you drift into a deeper sleep? At the very center of this swirling vortex lies the eye, a column of sinking air that creates a deceptive pocket of calm. Inside the eye, the winds may drop to a whisper and the sky might even clear, providing a brief, surreal reprieve from the surrounding chaos. This tranquility is walled in by the eye wall, the most violent part of the storm, where the highest wind speeds and heaviest rains are concentrated. While a hurricane represents a massive collection of energy, a single thunderstorm is a masterpiece of atmospheric physics and static electricity. Within the towering height of a cumulonimbus cloud, turbulent updrafts force ice crystals and frozen droplets called grapple to collide at high speeds. These collisions cause a separation of electrical charges, with positive charges gathering at the top of the cloud and negative charges pooling at the base. When the electrical tension between the cloud and the ground reaches a breaking point, a channel of ionized gas, or plasma, is forged through the air. This is a lightning strike, a discharge of electricity that can reach temperatures of 50,000 degrees Fahrenheit. This temperature is significantly hotter than the surface of the sun, causing the air in the lightning's path to expand with explosive speed. This expansion happens so rapidly that it creates a localized sonic boom, which we recognize as the rolling sound of thunder. It is a common misconception that thunder is the sound of clouds colliding, but it is actually the air itself vibrating from the sheer intensity of the heat. Every second, approximately 100 lightning bolts strike the Earth's surface, acting as a global electrical circuit that keeps the planet's atmosphere in a state of balance. These discharges also produce nitrogen oxides, which fall with the rain to provide essential nutrients for soil and plant life. Even in its most violent moments, the atmosphere functions as a sophisticated system of distribution, moving heat from the equator toward the poles and refreshing the Earth with every flash of light. High above this convective dance, a silent, invisible shield waits to intercept the sun's most energetic output. This is the realm of the ozone layer, a delicate concentration of triatomic oxygen molecules nestled within the stratosphere. While most of our air consists of diatomic oxygen, this three-atom variation possesses a unique molecular resonance that allows it to absorb the vast majority of the sun's harmful ultraviolet B radiation. Without this thin gaseous veil, the high-energy photons would reach the surface with enough intensity to break apart the fundamental bonds of organic chemistry. The stratosphere itself is defined by this interaction. As ozone molecules absorb ultraviolet light, they convert that energy into heat, creating a temperature inversion that stabilizes the global climate. This warming effect ensures that the atmosphere remains layered, preventing the chaotic mixing of the lower air from disrupting the quiet stability of the upper heights. The existence of this shield is the result of a continuous, self-renewing chemical cycle driven by the sun. When intense ultraviolet C radiation strikes a standard oxygen molecule, it splits it into two highly reactive individual atoms. These orphans quickly find other oxygen molecules to bond with, giving birth to ozone. It is a profound irony that the very radiation which poses a threat to life is the same energy used by the planet to forge its own protection. For decades, this equilibrium was threatened by the introduction of human-made chlorofluorocarbons, which drifted into the upper reaches of the sky. Once there, solar rays broke these chemicals apart, releasing chlorine atoms that acted as relentless catalysts. A single chlorine atom is capable of dismantling tens of thousands of ozone molecules, creating the famous thinning known as the ozone hole. However, the story of the ozone layer is also one of the greatest triumphs of modern science and international diplomacy. Since the implementation of global agreements to phase out these destructive chemicals, the atmosphere has begun a slow, steady process of self-repair. NASA and NOAA have documented a consistent trend of recovery, proving that the Earth possesses a remarkable capacity for resilience when given the opportunity to heal. This success provides a vital blueprint for how we might address other atmospheric challenges in the future. Have you ever looked up at a clear blue sky and wondered about the invisible chemistry happening miles above your head? This blue tint is the result of Rayleigh scattering, where shorter wavelengths of sunlight collide with nitrogen and oxygen, but the ozone layer adds its own subtle filtration to the spectrum. As we move even higher, beyond the chemical protection of the stratosphere, the atmosphere begins to thin into a ghostly plasma. Here, the air becomes so sparse that individual atoms are spaced widely apart, waiting for the solar wind to ignite them into the dancing curtains of light that decorate the polar nights. This ignition begins millions of miles away on the surface of the sun, where the solar wind originates as a constant stream of plasma consisting mostly of electrons and protons. These charged particles travel through the vacuum of space at speeds exceeding 1 million miles per hour, reaching our planet in roughly 2 to 4 days. As the solar wind encounters Earth's magnetosphere, it is largely deflected, creating a protective cavity in the streaming plasma. Some of these particles, however, find their way into the magnetosphere and become trapped within the Van Allen radiation belts circling the Earth in high-energy orbits. During periods of intense solar activity, such as coronal mass ejections, the magnetic field lines on the night side of Earth can stretch and suddenly reconnect. This process, known as magnetic reconnection, acts like a cosmic slingshot, accelerating electrons down toward the polar regions along the planet's magnetic field lines. When these high-energy particles finally reach the upper atmosphere, they collide with atoms of oxygen and nitrogen in a region called the ionosphere. These collisions transfer kinetic energy to the gas atoms, exciting their electrons into higher energy shells. As the excited electrons eventually return to their original lower energy states, they must release the excess energy in the form of photons. This constant cycle of excitation and relaxation produces the luminous, shifting glow that characterizes the aurora. Have you ever looked up at the stars and felt a deep sense of connection to the rhythm of the cosmos? Oxygen is the primary architect of the most familiar auroral color, a vivid yellowish green that occurs at altitudes between 60 and 150 miles. At much higher altitudes, typically above 180 miles, oxygen collisions result in a rare ethereal red glow that is often too faint for the human eye to perceive without long exposure photography. Nitrogen contributes different hues to the display, producing vibrant blues and violets when the molecules are ionized by incoming particles. If the neutral nitrogen molecules are struck lower in the atmosphere, they emit a deep crimson light that frequently appears as the jagged bottom edge of a moving auroral curtain. These displays are classified based on their location, with the aurora borealis illuminating the northern hemisphere and the aurora australis gracing the southern skies. Scientific observations have shown that these lights often appear as nearly identical mirror images at both poles simultaneously, a phenomenon known as conjugate auroras. The frequency and intensity of these events are dictated by the 11-year solar cycle, which moves between periods of solar minimum and solar maximum. During the solar maximum, the sun's magnetic activity increases, leading to more frequent geomagnetic storms and expansive light shows. These periods of space weather are carefully monitored by organizations like NOAA, as intense solar storms can impact satellite operations and GPS accuracy. Many listeners find that learning about these atmospheric interactions provides the perfect atmosphere for bedtime listening, offering relaxing facts to help you fall asleep. Historical records, like those of the 1859 Carrington event, remind us that auroras can occasionally reach as far south as the Caribbean. This science for sleep exploration reveals that while the lights appear silent, some researchers have documented rare acoustic signatures associated with thermal inversions during intense displays. Understanding the chemistry of the sky transforms a simple light show into a complex map of our planet's relationship with its parent star. Do you find the thought of such a dense, vibrant green forest to be more comforting in its abundance or mysterious in its many hidden layers? This biological density is also a hydrological force, as the trees release hundreds of gallons of water daily through their leaves. This moisture forms massive atmospheric rivers that travel across continents, proving that the health of these distant jungles is intimately tied to the climate of the entire globe. By moving water from the soil to the sky, these forests effectively act as a global cooling system. Do you find the thought of such a dense, vibrant green forest to be more comforting in its abundance or mysterious in its many hidden layers? This biological density is also a hydrological force, as the trees release hundreds of gallons of water daily through their leaves. This moisture forms massive atmospheric rivers that travel across continents, proving that the health of these distant jungles is intimately tied to the climate of the entire globe. By moving water from the soil to the sky, these forests effectively act as a global cooling system. Unlike the dense verticality of a forest, the beauty here is found in the horizontal, where the sky seems to stretch further than the eye can perceive. Grasses are the undisputed masters of this domain, having evolved a biological resilience that allows them to thrive where trees often falter. While a tree keeps its most vital assets in its trunk and branches, a grass plant hides its life force beneath the soil. Roughly 70% of a prairie plant's biomass is located underground in an intricate, tangled web of roots. This subterranean architecture allows the grasslands to survive extreme grazing and the frequent passage of fire. When a blaze sweeps across the savanna, it clears away the suffocating layer of dead organic matter and returns nutrients to the earth in a sudden burst of chemistry. Because the growing points of the grass remain protected by the cool soil, they can begin to sprout new green shoots within days of the flames passing. This regenerative cycle is a cornerstone of the ecosystem's health, preventing woody shrubs from encroaching on the open range. Have you ever looked out over a wide field and felt a strange sense of belonging in that openness? Across these rolling plains, life is defined by constant motion and the pursuit of seasonal rains. In the Serengeti, over 1 million wildebeest and hundreds of thousands of zebras engage in a circular migration that tracks the growth of fresh grass. This movement is not merely a search for food, but a complex interaction that keeps the soil fertile through natural fertilization. The Eurasian steppe acts as a massive land bridge stretching from Hungary to China, characterized by a climate of sharp extremes. Here, the grasses must endure bone-chilling winters and blistering summers, leading to the development of deep, rich soils known as chairnisms. These black earths are among the most fertile on the planet, holding vast amounts of sequestered carbon within their dark depths. If you find these relaxing facts helpful for your bedtime listening, perhaps you would like to subscribe to continue our quiet journey through the natural world. The sheer scale of these landscapes provides a unique habitat for specialized herbivores, such as the saiga antelope, whose unusual nose filters out the thick dust raised by the herd. Every species here has adapted to a life without cover, relying on speed, camouflage, or the safety of the group. As the wind ripples through the tall blades, it creates an undulating wave known as a mar de grass, or sea of grass, a rhythmic motion that mimics the tides of the ocean. In this environment, the horizon is not a boundary, but an invitation to witness the endless persistence of life under the open sun. Because it remained secluded for such a staggering duration, approximately 90% of its wildlife evolved in complete solitude. The lemurs found there are a prime example, branching out into dozens of specialized forms to fill ecological niches that monkeys occupy elsewhere. This ancient island serves as a living museum, preserving lineages that have long since vanished from the larger continents. Because these species cannot interbreed with their distant relatives, they become highly specialized, fine-tuned to the specific temperature, soil, and flora of their island home. In contrast to these old continental pieces, volcanic islands like the Galapagos rise directly from the seafloor, born from the fiery depths of oceanic hotspots. These islands start as barren basaltic rock, waiting for the wind or the currents to bring the first intrepid pioneers. Charles Darwin famously observed that the finches on these islands developed varied beak shapes, each perfectly adapted to the specific food sources available on their respective outcrops. It is fascinating to consider how a single ancestral species can radiate into so many different forms simply because of the physical barriers created by the sea. Have you ever wondered which remote island you would choose to visit if you could see these evolutionary wonders firsthand? Life on these secluded patches of Earth often undergoes dramatic physical transformations known as island dwarfism and island giantism. When large mammals, such as elephants or deer, find themselves on small islands with limited food supplies, natural selection often favors smaller body sizes over many generations. This creates miniature versions of once massive creatures, allowing them to survive on significantly fewer calories within a restricted territory. Conversely, smaller animals like rodents or reptiles may grow to unexpected sizes when they arrive on islands devoid of their natural predators. Without the need to hide in small crevices or expend energy escaping hunters, the biological constraints on their growth are often lifted. The giant tortoises of the Aldabra Atoll or the formidable Komodo dragons of Indonesia are a testament to this liberation from the standard rules of biology. These isolated ecosystems demonstrate that the path of life is never fixed, but rather a flexible response to the specific geometry of the land. As we look at these emerald dots scattered across the deep blue, we see a map of possibilities where time and distance have sculpted the extraordinary. Over 9,000 plant species are packed into this small corner of the world, with roughly 69% of them being entirely unique to the region. Many of these plants, like the iconic king protea, have evolved a remarkable relationship with wildfire, using the heat of the flames to crack open their seed pods. Have you ever noticed how some plants in your own garden seem to thrive only after a period of intense struggle or change? In the fynbos, the ash from these fires provides essential nutrients to the nutrient-poor soil, allowing a fresh generation of life to emerge from the blackened earth. If the fynbos is a terrestrial treasure, the coral triangle serves as the global epicenter of marine life, spanning across the waters of Southeast Asia and the Western Pacific. This underwater realm contains nearly 600 different species of reef-building corals, which is about 75% of all known coral species on Earth. The biological productivity here is fueled by complex currents that mix nutrient-rich waters, supporting thousands of species of reef fish. Within these submerged cathedrals, the balance is maintained through intricate symbioses, such as the relationship between nitrogen-fixing bacteria and the coral polyps themselves. If you find these intricate connections fascinating, subscribing to the channel helps ensure more of these scientific stories can be shared. The stability of these hotspots relies on highly specialized food webs, where the removal of a single keystone species can trigger a trophic cascade. In these environments, energy flows through pathways that have been refined over millions of years of co-evolution. Each predator, prey, and decomposer acts as a structural pillar, holding up the roof of the ecosystem. When we protect these concentrated pockets of life, we are not just saving individual animals or plants, we are preserving the genetic blueprints of our planet's resilience. Now, let us look beneath the surface at the living skin of the world, where soil breathes and pulses with a quiet, hidden energy. Far from being inert dirt, soil is a biological engine that sustains nearly every terrestrial life form we know. If you were to scoop up a handful of earth from a forest floor, you would be holding an entire universe of complexity in your palm. In a single gram of healthy soil, scientists have found billions of bacteria belonging to thousands of different species. These microscopic architects work tirelessly to break down minerals and organic matter, recycling the old into the new. Do you remember the last time you walked barefoot on soft, cool earth and felt that grounding connection to the land? This thin layer of topsoil is responsible for filtering our water and providing the nutritional foundation for every fruit and grain we consume. Beneath the forest floor, a vast silver-white network of fungal threads known as mycelium creates an intricate communication system. This mycorrhizal network connects the roots of different plants, facilitating a mutual exchange of sugars and minerals. This partnership is so profound that many trees are unable to survive without their fungal companions providing essential phosphorus and nitrogen. Some researchers refer to this as the wood wide web, a decentralized intelligence that manages the health of the entire grove. Through these threads, older mother trees can shuttle extra nutrients to saplings struggling in the shade. It is a slow, silent conversation occurring right beneath our feet, where cooperation often outweighs competition. While fungi handle the heavy lifting of decomposition, bacteria manage the chemistry of the air and earth. Nitrogen makes up about 78% of our atmosphere, yet plants cannot use it in its gaseous form. Specialized soil bacteria bridge this gap by fixing nitrogen into ammonium and nitrates, effectively fertilizing the planet from within. This elegant cycle is a cornerstone of global ecology, ensuring that life can continue to regenerate season after season. Despite its immense power, soil is incredibly fragile and slow to recover from damage. It can take up to a millennium to form enough soil to sustain a diverse meadow, as rocks are slowly pulverized by wind, water, and the patient roots of lichen. Soil also serves as one of the planet's most significant carbon reservoirs, locking away vast amounts of carbon dioxide that would otherwise warm the atmosphere. When we look at the soil, we are seeing the history of the Earth compressed into a dark, rich substance. It is a mixture of minerals, air, water, and the remains of countless generations of living things. This substance is tiered into distinct layers called horizons, each representing a different stage of geological and biological transformation. The top layer consists mostly of organic litter like fallen leaves and twigs. Below that, the topsoil is where the most intense biological activity occurs. As we learn more about these relaxing facts and the science for sleep, we realize that our survival is inextricably linked to the health of this microscopic frontier. This hidden world ensures that the cycle of life remains unbroken, turning the end of one organism into the beginning of many others. Every handful of earth is a testament to the patient, persistent work of nature over millions of years. To understand our world, we must move beyond human calendars and embrace the staggering concept of deep time, which spans 4.5 billion years of planetary history. This chronological scale is so vast that it dwarfs the entirety of written human records, placing our existence within a much grander, slower narrative of tectonic shifts and evolutionary transformations. We perceive the passage of time through the changing of seasons or the growth of a tree. Yet the Earth measures its age through the steady accumulation of minerals and the gradual cooling of its core. This history is etched into the very crust of the planet, where layers of sedimentary rock serve as a physical archive of everything that has ever transpired. The science of stratigraphy allows us to read these layers, revealing how ancient environments shifted from shallow seas to arid deserts over millions of years. According to the law of superposition,
The youngest rocks are found at the top of a sequence, while the oldest reside at the bottom, creating a vertical timeline that reaches back to the dawn of the world. Within this timeline, geologists have identified distinct chapters known as eras, each defined by unique biological and geological milestones. The Paleozoic era, often called the Age of Ancient Life, began roughly 541 million years ago and saw the first great diversification of complex organisms in the oceans. It was during this period that the first plants took root on land and the earliest ancestors of modern insects began to fill the air. Following a massive extinction event, the Mesozoic era emerged, famously known as the Age of Reptiles or Dinosaurs.
For nearly 180 million years, these creatures dominated the terrestrial landscape, while the supercontinent of Pangaea slowly drifted apart to form the familiar shapes of our modern continents. The transition into the Cenozoic era, which continues to this day, marked the rise of mammals and the development of the vast grasslands that define many of Earth's ecosystems. This most recent era has been characterized by significant climatic shifts, including the repeated advance and retreat of massive ice sheets during the Pleistocene epoch. When you stand before a canyon wall or hold a smooth, ancient stone in your palm, do you find it easier to sense the weight of these billions of years, or does the scale feel more tangible when you look up at the light of distant stars? These moments of reflection help us appreciate that we are living on a planet that is constantly recycling itself, turning the dust of the past into the foundations of the future. Every grain of sand on a beach was once part of a towering mountain range, and every mountain was once a collection of sediments at the bottom of a forgotten sea. This endless cycle ensures that the Earth remains a dynamic, evolving atlas, where the story of life is continuously being written in the enduring silence of the stone. Yet this record is punctuated by profound moments of silence where the pulse of the planet seemed to falter. Geologists identify 5 major intervals known as the Big Five mass extinctions, where the vast majority of existing species vanished in a geological blink. The most devastating of these occurred roughly 252 million years ago at the end of the Permian period. This event, often called the Great Dying, saw nearly 96% of marine life and 70% of terrestrial vertebrates disappear. Massive volcanic eruptions in what is now Siberia released staggering amounts of carbon dioxide, leading to runaway global warming and ocean acidification. It took millions of years for ecosystems to stabilize, yet the void left behind eventually sparked an explosion of new biological forms. Life possesses an incredible, stubborn persistence that allows it to reclaim even the most desolate landscapes. About 66 million years ago, a massive asteroid, roughly 6 miles wide, struck the Yucatan Peninsula with the force of billions of atomic bombs. This Chicxulub impact sent a shroud of soot and dust into the atmosphere, blocking the sun and halting photosynthesis for years. While the non-avian dinosaurs perished, small burrowing mammals found sanctuary beneath the charred surface. These survivors emerged into a world of empty niches, eventually diversifying into the countless forms we recognize today. Every catastrophe on Earth serves as a harsh pruning process that redirects the flow of evolution toward unexpected horizons. Have you ever wondered which ancient creature you would most like to see brought back to life if you could view it from a safe distance? Even the Ordovician Silurian extinction, triggered by a sudden ice age and falling sea levels,
couldn't permanently quiet the seas. Recovery often begins with generalist species, those hardy pioneers capable of thriving in unstable conditions. Over time, these pioneers specialize, rebuilding the complex webs of interdependence that define a healthy biosphere. The late Devonian extinction primarily affected marine life, wiping out many coral reef systems and early armored fish known as placoderms.
Scientists at the Smithsonian Institution note that this was likely caused by a combination of falling oxygen levels in the oceans and rapid climate shifts. Despite such losses, the Triassic-Jurassic extinction later paved the way for the age of dinosaurs by removing competing groups. The fossil record shows that after every pulse of destruction, the diversity of life has eventually exceeded its previous peaks. This resilience suggests that our planet is not just a stage for life, but an active participant in its survival. Each layer of sediment from these eras tells a story of tragic loss, followed by an almost defiant renewal. The Earth acts as a self-correcting system, balancing the chemistry of air and water to foster new beginnings. We exist because of these narrow escapes and the remarkable adaptability of the organisms that came before us. This endurance is mirrored in the way the planet manages its own internal heat. Within this internal heat, a new signature has emerged, one that defines our current geological epoch with startling clarity. This force reshapes the world from the outside in, marking the beginning of what scientists call the Anthropocene. If you were to look down from the height of the International Space Station, the most immediate evidence of this shift is the electric web of light that clings to the dark side of the globe. These glowing veins tracing the coastlines and river valleys represent a massive redistribution of energy that never existed before the last 2 centuries. Unlike the steady, ancient glow of volcanic activity, this artificial luminescence follows the intricate logic of human commerce and settlement. Beyond the lights, the very skin of the planet has been restitched into a patchwork of geometric precision. Nearly 40% of the ice-free land surface is now dedicated to agriculture, a transformation that has replaced the chaotic, fractal patterns of wilderness with the hard lines of monocultures and irrigation grids. From above, these vast green and gold rectangles look like a digital skin stretched over the rolling topography of the continents. This reorganization extends into the 3rd dimension through the creation of urban heat islands. In these dense concentrations of glass, steel, and asphalt, the Earth's surface loses its ability to reflect sunlight effectively. Instead, the dark materials absorb solar radiation throughout the day and release it slowly throughout the night, keeping city centers significantly warmer than their rural surroundings. This localized climate shift is so pronounced that it creates its own wind patterns and alters the local water cycle. Have you ever noticed how the air feels slightly heavier and warmer when you move from a park into a dense city street late in the evening? Underpinning all of this is the technosphere, a term researchers use to describe the totality of human-made objects currently in existence. This layer, estimated by scientists at the University of Leicester to weigh roughly 30 trillion tons, includes every skyscraper, smartphone, paved road, and plastic bottle ever manufactured. It is becoming a permanent part of the Earth's crust, a distinct stratigraphic layer that future geologists will recognize by its unique chemical and physical signatures. We are seeing the birth of new minerals such as plastiglomerates, which form when plastic waste melts and fuses with natural sediment and volcanic rock.
Even the composition of the atmosphere has been altered as the burning of fossil fuels releases carbon that had been sequestered underground for hundreds of millions of years.
This rapid cycling of ancient carbon represents a profound break from the slow, rhythmic pulses of the natural carbon cycle. As these changes accumulate, the geography of the Earth is no longer just a product of plate tectonics or erosion, but a reflection of human movement and industry. The maps of the future are being drawn not just by the movement of the tides, but by the placement of our foundations. This human-centric geography is now a global constant, influencing the migration of birds and the flow of rivers alike. The footprint we leave is deep, heavy, and increasingly indelible. We have traveled from the crushing gravity of the iron core to the edge of the vacuum, crossing tectonic boundaries and following the invisible paths of deep-sea currents. Our planet functions as an integrated masterpiece of physics and chemistry, where the slow churning of magma deep beneath your feet provides the magnetic shield that preserves the very air you breathe. This unity defines the Earth. No part exists in isolation, from the silicate rocks of the mantle to the nitrogen-rich atmosphere that scatters the light of distant stars. These relaxing facts serve as a reminder that the world is a closed system, a self-sustaining vessel moving through the silence of the cosmos. As the sun sinks below the horizon, the energy absorbed by the oceans throughout the day begins its slow release, maintaining the thermal equilibrium that allows life to flourish. Even in the stillness of the night, the Earth is an engine of constant, quiet activity. The carbon cycle continues its work as forests respire, and the great conveyor belt of the ocean moves water from the tropics to the poles, ensuring that the climate remains within the narrow margins required for our survival. This inherent stability is the foundation of science for sleep, providing a reliable backdrop for our rest as the planet rotates at over 1,000 miles per hour at the equator. Gravity holds every molecule of the atmosphere in place, shielding us from the cold expanse of space with a gentle, invisible hand. The same laws of thermodynamics that govern the cooling of a cup of tea are at work on a planetary scale, slowly radiating heat into the void. The Van Allen radiation belts act as a secondary barrier, trapping charged particles from the solar wind and preventing them from stripping away our protective ozone layer. Within this delicate shell, the biological and geological worlds are inextricably linked, with microorganisms in the soil influencing the composition of the clouds above. How often do you find yourself looking up at the moon and wondering about the hidden mechanisms that keep our world so perfectly balanced? This curiosity is the spark that drives every scientific discovery, inviting us to look closer at the soil beneath us and the sky above. As we conclude this exploration of our endless atlas, let the vastness of these systems offer a sense of perspective and quiet wonder. The resilience of our world is matched only by its complexity, a testament to the billions of years of evolution and geological transformation. If you have enjoyed this journey through the mechanics of our home, please consider subscribing to join our community of curious minds for more bedtime listening. There is always more to discover in the quiet corners of the universe, and the pursuit of knowledge never truly ends. May the steady, ancient rhythms of the Earth accompany you as we remain part of this singular, beautiful, and pale blue dot.